Hi guys, welcome you all to my channel Explore Edu to Teach.
So in this class, we'll be solving certain numericals related to EDC. We have already learned some basic concepts of EDC. Those videos are uploaded in my EDC playlist on my YouTube channel. Please go and watch it from there. If you know those concepts, it will be easier for you to solve the numericals on it. So we'll be solving today some gate problems which were asked, and there are three numericals which we'll be solving. They are basic numericals with basic concept. So if you know the basic concept, solving this numerical is going to be easy. Generally, EDC is one of the most core concepts, the core subjects of electronics and communication department or some allied branches of engineering. So normally students are very afraid to solve questions on EDC, and they feel that even competitive exam like GATE asks very difficult question. But today when we try to solve certain questions, you will realize that if not all, majority of questions in EDC are formula based or conceptual based. If you know the basic concept, if you know the basic terminology, you can solve this question and gain marks for them. So we'll try to understand those. If you haven't watched the video, please go and watch it out. They are basic videos. They are very important in order to learn this subject. In those videos, if you see, we have spoken about a lot of concepts such as the introduction, the type of materials, the type of semiconductors, what are the terminologies involved in that, what is a Fermi energy level, how is the Fermi energy level classified for different types of semiconductor, what is a Fermi direct distribution, and now we'll be solving certain gate questions. So please go and watch those videos. They are short videos, not very long videos, hardly 10-15 minutes video. It's going to be very helpful for you. The notes are present in the description box of the YouTube videos. So please go and watch it from there. Make a note of it, and then you can always try to understand these numericals that we are going to today solve. So let us try to solve the first numerical. What does the numerical say? A silicon bar, okay, a semiconductor bar, is doped with donor atoms. So what do you mean by donor atoms? It's a N kind of semiconductor. Had it been acceptor atoms, it would have been a P kind of semiconductor. And the donor atoms concentration is given as Nd is equal to 2.25 into 10 raised to 15 atoms per centimeter cube. Given the intrinsic carrier concentration of silicon at T is equal to 300 Kelvin, the intrinsic concentration Ni is given as 1.5 into 10 raised to 10 per centimeter cube. Assuming complete impurity ionization, the equilibrium electron and hole concentration are. So please try to understand this concept very well. Understand the symbols and the terminology used. There is a silicon bar. The donor atoms is given as Nd, which is equal to 2.25 into 10 raised to 15 atoms per centimeter cube. There is an intrinsic carrier concentration at 300 Kelvin, which is given as Ni is equal to 1.5 into 10 raised to 10 per centimeter cube. Now if you assume complete ionization, what is going to be the electron and the hole concentration? So if you see over here, I have given the page numbers also over here for you to refer the formulas. So in page number 9, if you see, we have written this formula over here. Ni square is equal to Np. This is a very basic formula in EDC, which is majority time asked. So you should have an idea about that. So the question says a silicon bar is there. It is doped with Nd, which is given as 2.25 into 10 raised to 10 raised to 15 atoms per centimeter cube. There is a Ni mentioned, that is the intrinsic carrier concentration. And then they are giving the values of electron and hole concentrations. So in the N type of semiconductor, the Nd is given as 2.25 into 10 raised to 15 atoms per centimeter cube. And now they are asking you the electron and the hole concentration. See, if it's an N type of semiconductor, the electron concentration is equal to Nd only, which is given as 2.25 10 raised to 15 per centimeter cube. And the hole concentration can be given with the formula Ni square is equal to Np, therefore P is equal to Ni square by N. So the Ni square, so the Ni value is given over here as 1.5 into 10 raised to 10, and the N value is also given over here. So you can find out the whole concentration finally. I hope I'm very clear with this. The next question. At T is equal to 300 Kelvin, the whole mobility is given as mu P is equal to 500 centimeter square per volt second. The kT by Q is equal to Vt. These terminologies are all explained in my previous video. Hence, I was advising you all to please go and watch out those videos if you haven't watched those videos, because then those terminology will help you to understand the terms given over here and get the solution to the question. So the Vt or kT by Q is given as 26 millivolt. The whole diffusion constant dP is what? So basically in a p type of semiconductor, dP by mu p is equal to Vt. Therefore, dP is equal to mu p into Vt. Now what my mu p is given as? The mu p is equal to 500 centimeter square volts per volt second. And the Vt is given as 26 millivolts. Therefore, dP is equal to 13 centimeter square per second. Similarly, for an N type of semiconductor is given as dN by mu1 is equal to Vt. Now let us solve the final question. The question reads, a silicon sample doped with Nd. Nd, you understand, it's an N kind of semiconductor. 10 raised to 15 per centimeter cube donor atoms. The intrinsic concentration Ni is given as 1.5 to 10 raised to 10 per centimeter cube. Now what is happening is that the sample which is already doped with Nd is now additionally doped with Na, and Na is given as 1 into 10 raised to 18 per centimeter cube. The approximate number of electrons per centimeter cube in sample is what? So try to understand this question. What it's asking is the value of N. Had they given holes per centimeter cube, it would have been P. So as the question says, initially the semiconductor is doped with Nd. Hence it becomes a N kind of semiconductor. Now in this N kind of semiconductor, it has been doped with Na. So if you see the value of Nd, Nd is 10 raised to 15. Na is 10 raised to 18. So since my Na is greater than Nd, it becomes a P kind of semiconductor. Had by Nd being greater than Na, it would have been a N kind of semiconductor. So my P is equal to Na is equal to 10 raised to 18 per centimeter cube. Now N is equal to Ni square by P. The Ni square, the Ni is given as 1.5 to 10 raised to 10. And the P value is nothing else than Na, and from that you will get the value of N, which is 225. So I hope I am very clear. So you should know what do you mean by Nd. Nd means the donor atoms, that's the N kind of semiconductor. You should know what do you mean by Ni. Ni is the intrinsic carrier concentration, that is 1.5 to 10 raised to 10 per centimeter cube. Finally you will get the value of electrons and hole concentration. Similarly, you have the value of mu p given, Vt given, you will get dP also. Similarly, you have this concept also over here. So I hope I am very clear with this. So if you like this video, do not forget to like, share, subscribe to my YouTube channel. Share it to as many friends and your college mates you feel can get benefited out of it. It's a very important concept and it is used in your 11th and 12th grade also, in your engineering also, in your diploma also, and for your competitive exam preparation also. So please like, share, subscribe to my YouTube channel and follow me on Instagram as well. I will be posting all the formula sheets on my Instagram page. It will be very handy for you to prepare for numericals and especially at the time of your exam to revise for the formulas, because there are many formulae in this. So I'll try to put it on my Instagram page in a very concise manner so that it can be very easy for you to just go through it and revise it in a faster manner. So the links of my Instagram page are put down in the description box. Please go and watch my Instagram page, and if you like it, do not forget me to follow me on Instagram as well. Thank you so much guys. God bless.